we're kind of playing with the due date because there is Thanksgiving in the middle, and I really don't want you to be working during the break. So we'll try to maybe add a day or two extra here. Other than that, oh, and your homework 4, we are about halfway through grading it, and we should be done with it hopefully soon. And your project reports as well, I'm in the process of reading them. I should be giving you feedback by, say, at best Saturday. So in the meanwhile, I encourage you to just continue with your projects, and as when the feedback comes by, you can kind of reorient your projects. Alright, any questions about any of these mechanics? Any questions about the class so far? Looks like it's going to be a smallish class, so maybe we can have more conversations today. In the last lecture we started the section on probabilistic learning. And just to remind you, the question that motivates this is the same question that has been motivating the entire class, the entire semester. How do we define learning? If I care about finding a classifier that's the best classifier, how do we define best? And if you start from a probabilistic definition, using Bayes' theorem, we can have, Bayes' theorem gives you a clean definition of best. And we saw that there are two, flavors of this definition. One of them is called maximum a posteriori learning, which says the classifier that is best is the one that has the highest posterior probability when you given the data. The probability, the hypothesis that is to be chosen according to this rule is the one that has the highest value of the probability of the hypothesis being the true one given the data set. And a tweak on maximum a posteriori learning gives you maximum likelihood learning. Maximum likelihood says, I don't know any prior knowledge about the hypothesis space, so let me assume that all the hypotheses are equally likely and apply the maximum a posteriori rule. Under that situation, you pick the classifier that has a maximum likelihood. And we worked through a couple of examples of this, and I asked you to go back and work out these examples again, just to show yourself that it works. Are there any questions about this? The one interesting thing that we saw at the end of the last lecture was that actually if you start off with a certain assumption about how the data is generated, you can write down linear regression, the Bayesian interpretation. We saw the Bayesian interpretation of least squares regression. It turns out the least squares regression could have been entirely derived by starting off with a certain probabilistic assumption and just following through the mechanics. And that gave us two interpretations for linear regression. We could have seen that as loss minimization, where we say, I don't know how the data is generated. I don't care how the data is generated. I'm just going to assume that my hypothesis class is linear, and try to find one that minimizes the squared error on the training set. That gives you least mean squares. It turns out you could get to the same thing by saying that you believe that the errors are normally distributed, and we apply maximum likelihood estimation. At the end of the day, the actual optimization that you solve to get the best hypothesis ends up being the same. It's just a perspective that changes. Any questions about any of this? About Bayesian learning in general? What Bayesian learning means? Okay, so in the absence of any questions, let's move ahead. Today we are going to look at this theoretical construction called the Bayes optimal classifier. It's just a convenient thing to think about, just this perfect classifier, almost perfect classifier that we cannot really get, but it's useful to think about this object because this is the one that in many cases, this is the best we can do. So, in order to motivate Bayes optimal classification, we need to think about how we make decisions slightly differently. So far, what we've been doing is you're given a training set and we find the most probable hypothesis, the best hypothesis. And then you fix the hypothesis, and when a new example comes in, you go around making predictions using this fixed hypothesis. Instead, we could ask, I'm not going to actually pick a hypothesis at all. Instead, I'm going to keep my entire training set. When a new example comes in, I'm going to ask, what is the most probable label given the training set? Subtly different. It's not the same as using the you sticking to a hypothesis and then making predictions. Let me give you an example. Suppose your hypothesis space has only 3 functions, h1, h2 and h3. These are the 3 classifiers that we need to choose from. And let's say you have some data set D, and doesn't matter how we get these numbers, let's say we know that the the posterior probability of h1 given D is 0.4. The posterior probability of h2 and h3 given D are both 0.3. Now, what's the map hypothesis according to this? The most probable hypothesis according to these numbers. Must be too early. There's an obvious answer here. H1. Thank you. H1. That's easy. I mean, there are no trick questions in this class, unless it is a trick question. All right. So, instead of thinking of the most probable hypothesis, let's say, actually no. Let's continue with this. Let's say you pick your hypothesis and a new example comes in. The most let's call that, what did I call it, X, and H1 predicts a positive and H2 and H3 predict negative. First of all, what is the prediction of the map classifier? What's the map classifier? It's H1. So the prediction, so this one here is the map hypothesis. H1. So the prediction of H1 is plus. So on this example, had you chosen the classifier according to the map principle, it would have predicted plus. On the other hand, I could ask, what is the most probable label for X according to this hypothesis space? So the probability that the label is plus is 0.4. Why? Because you can get plus only through H1. On the other hand, H2 and H3 both predict minus. And the probability that the label is minus is 0.6. So, probability of plus given H1 equals plus, equals 0.4, which means map classifier predicts plus, because we've chosen H1 to be the map classifier. On the other hand, if we did not pick H1 as the true classifier, instead we entertained all the hypotheses until the last minute. Everything's in play, then you could compute the value, the probability that the label is plus, and that's 0.4, and the probability that the label is minus is influenced both by H2 and H3, and together they add up to more than what the probability of plus. Does that make sense? Is the difference, first of all, is the difference clear? Does the difference make sense? Questions? Yes?
So you're saying, even though H1 has the highest probability of being correct, if you take all 3 together, given the labeling, it may be that the combination of H2 and H3 are correct.
It's not a question of correct or not. We don't know what the true label is.
Okay.
H1 is the classifier that has the highest probability of being the true one. That's the map classifier. On the other hand, if I do not commit to H1 being the classifier, instead I decide to consider every possible classifier until the last minute and entertain all their predictions, and their predictions are weighted by the probability of that classifier being the correct one, then the label minus becomes higher, more probable. So there is a difference between the most probable classifier and the most probable label. Does that make sense? The most probable classifier is H1. H1 predicts plus. On the other hand, the most probable label is minus, which is so weird. It may seem like a counterintuitive thing, but here's a very simple example that shows it's possible.
Are we going to be implementing?
Good question. You can't. This classifier, this most probable classification, is called the Bayes optimal classifier, the Bayes optimal label. You can think of this entire thing here to be a classifier. You can think of it's a hypothesis space. The hypothesis space here is the set of every possible. You entertain the entire capital H hypothesis space. You integrate over the entire hypothesis space to get this label, and you can't do that because the hypothesis spaces are often infinite or extremely large. So, in order to motivate the Bayes optimal classifier, we should ask, how do we use this general formulation? The Bayes theorem gives us a way of thinking about classification, and the Bayes optimal classifier stems from a question of how do we use this Bayes theorem or the general idea of probabilistic classification to define learning. Your hypothesis space could be the collection of functions. That's what we've been doing so far, right? Your hypothesis space is just a collection of functions. Given a training set, you can choose the best function, freeze that function, and use that to make decisions. That's what we've been doing so far. You have a training set, you use the training set to get a classifier, you freeze the classifier, and then you use the classifier in the future. Another option is you do not pick a classifier. Instead, when you keep the training set, and then when a new example comes in, you don't have a classifier. Instead, you try out every possible classifier in the hypothesis space. Each of them gets a vote. The vote is the probability, the posterior probability of that classifier. And then you try to choose the optimum, the prediction as the weighted, as the one that gets the highest vote or the highest probability. These two can be different, as we just saw in the example that we saw. So, to make it more formal, the Bayes optimal classification is the label that's produced by the most probable. It's the most probable label that can be. Okay, so there's a mistake here. Defined as the most probable label. In other words, if I want to find a label, I try out every possible hypothesis in the hypothesis space, get the probability of the label given the hypothesis, that particular hypothesis, and weight it by the posterior probability. This is posterior probability of Hi given the data. And I write summation here, but if your hypothesis space is real valued, this becomes an integral. So in order to make one prediction on one example, you have to integrate over the entire hypothesis space. This is, of course, it's hopelessly inefficient. It tends to be an interesting theoretical concept because in general, on an average, in a formal sense, there is no classifier that can outperform this using the same set of hypothesis space and using the same prior knowledge. By prior, I mean the prior as defined by the Bayes theorem, which is cool, but we can't do. So the story is we can't do better than this, but we can't do this either. So we go back to map classification. This is just a theoretical construct that is useful to know. This is called the Bayes optimal classifier. Questions? Yes.
So, is there like a more practical form of this where you just pick
A subset.
a subset?
Yeah, you could. In fact, one way of interpreting an ensemble could be through this lens, right? You could interpret it through this lens, but not exactly, because you don't actually deal with probabilities there. But this can be one way of thinking. Instead of the summation, instead of integrating 100, and you keep the 100 best in some sense, for example. Or you could sample. When a new example comes in, you could do some sampling. So those are, useful. In some sense, this is a useful idea to drive innovation. If your classifier is not good, you could try keeping more than one in play. If you don't have the entire hypothesis space, but you have 3 of them, you have 3 functions. Let's say you don't keep the entire set of weight vectors. You don't integrate over the entire space of all the weight vectors. Instead, you keep 300 weight vectors. And when a new example comes in, you ask each of them to vote. And you remember also what was the probability of each of those weight vectors given the training set. That is fixed because that's not going to change. So the thing inside the box is not going to change when a new example comes in. So you can pre-compute that. So these kinds of tricks are possible, and they tend to be slightly more robust if more expensive though. Other questions? Questions about Bayesian learning in general? If not, we're going to switch gears slightly to what could be called, yes, there's a question.
How do we know the posterior probability?
Hold on. How do we know
Right.
this term here?
Yeah, how would we know that?
How do we know that? That's basically map. It's the same way that we know the. Let's think about what is map learning. Map also requires you the same thing. I'm not giving you an answer to the question. I'm saying that in order to, if we had to solve map, we have to do this anyway. H map is argmax over H, P of H given D, right? This is also the posterior probability. The only way we know this is through the Bayes theorem. This is proportional to P of D given H times P of H. This is your likelihood, and this is your prior. And your prior is something that you assume. And the fundamental thing in Bayesian learning is you need to have some way of writing down the likelihood function. That's your modeling choice. You need to do, as a part of defining the space of models to entertain, you need to define how a classifier, a hypothesis, would generate a data set. Because if you knew how a classifier could generate a data set, using this combination, you've got the posterior. Which is why you often see Bayesian classification, Bayesian learning starting off with what is called a generative story. It's a story of how a classifier could generate a data set in a probabilistic sense. That's your modeling choice. We'll see one of those choices right now. Other questions? Any half hands raised? Everyone puts their hand. Alright, let's move to the next space here of a particular choice of how data might be generated given a hypothesis space. So we're going to talk about the naive Bayes classifier. Typically, very often, when people think Bayesian learning, they automatically think naive Bayes classifier. Not entirely the greatest idea, but it's so simple to implement and so simple to learn that this ends up being the first classifier for many people. So we're going to take a look at what the naive Bayes classifier is, how we can learn it. If time permits, we'll get into practical concerns and we'll get into one of these other big ideas in machine learning, which is the difference between what is called generative and discriminative models. And this will give us a good segue to logistic regression, because the naive Bayes is going to be our first generative model that we see. Alright, so we've seen Bayesian learning. Bayesian learning is the idea that we use a probabilistic criterion to select the best hypothesis. And we saw two kinds of probabilistic criteria, maximum a posteriori and maximum likelihood. What's the difference between them? Yes?
Domain knowledge of the hypothesis.
More formally?
The function giving probabilities to each function of how likely they are to do well.
So the prior.
The prior.
So the only difference between these two is maximum likelihood has an implicit assumption that there is the prior over the hypothesis space is uniform. There's a uniform prior over the hypothesis space. So instead of that's Bayesian learning. You could also be Bayesian in your prediction. You could also, what that means is, you could also be, you could learn your hypothesis space itself could be functions that predict probabilities. Right? The hypothesis space earlier was functions that predicted, pluses or minuses, true or false. Instead, your hypothesis space itself could predict probabilities, and you can use these probabilities to pick a label. You could be Bayesian in your prediction. You could ask for the most probable label given a particular hypothesis. This is called maximum a posteriori prediction. It's different from maximum a posteriori learning. In maximum a posteriori learning, you are asking what is the most probable hypothesis given a data set. In maximum a posteriori prediction, you are asking what is the most probable label for a particular example given a hypothesis. Does the difference make sense? So here in map learning, we are asking what is argmax over probability of hypothesis given the data set. Here we are asking what is the probability of the label given an example and a particular hypothesis. This data set here consists of many examples. And this, even if it seems perfectly clear right now, it will get confusing, I assure you, because we will use map learning to learn classifiers that we'll use which will predict using map prediction. So these two things, try to, if there are any questions about this, you can please ask right now, or you can ask later also. Yes?
So what do you mean by the probability is uniform over the hypothesis?
That is for maximum likelihood learning.
Yeah.
So what is probability of the hypothesis given the data set? This is map learning asks best find hypothesis such that find hypothesis using the following. I'm not going to write the whole thing. Such that you maximize the probability of the hypothesis given the data. But what does this mean? This is, or let's say argmax over hypothesis. But this is exactly the same as argmax hypothesis probability of data given the hypothesis times probability of hypothesis. This is by Bayes rule. Now, on the other hand, if the probability of the prior is constant, then best hypothesis, let's say, equals argmax or hypothesis probability of data given the hypothesis. Right? Now, this part here at the bottom is called maximum likelihood. Why? Because this term here is the likelihood of the data. If the priors were uniform, then maximum likelihood estimation, estimation is the same as maximum likelihood estimation. In fact, you can define maximum likelihood estimation as map learning with uniform priors. Because uniform priors would be the, so think of why your priors might be uniform. If you do not have any domain knowledge, for example, if you don't know anything about which classifier is better than the other and you don't care, all of them are equally likely in the absence of any information. If that's what you believe, then you're doing maximum likelihood estimation.
That will be only in the first step. It will keep on updating. We'll have a new priority every time.
No, priors are fixed. Right? There's no steps here. I'm talking about the optimization problem. We haven't come to algorithms yet. There are in fact, all of the last lecture, if I remember correctly, we did not talk about any algorithms. Right? We talked about the concepts. The priors are fixed. The priors do not depend on the data. So this is a function that does not have d inside it. Right? This thing here. It does not have d, so it's fixed. It does not depend on any data set. Okay, so let's look at how the idea of maximum a posteriori prediction plays out. We can use the Bayes rule for predicting the label given an example. So let's say you're given a new example, x. We could ask which label is the most probable. In order to do that, we can ask, in other words, we can ask what is the posterior probability of the label being y when the example is x. And we can be Bayesian about it. In other words, we can ask the posterior probability is the likelihood of that example being the true example for that label times the prior divided by probability of x. And you could predict the label. You can predict the label that has the highest posterior probability. Keep in mind, there is implicitly here there is a hypothesis. The probabilities define the hypothesis in this case. But if I'm predicting in this way, the denominator is a constant. The denominator does not depend on y at all. You're maximizing over y. The denominator doesn't depend on y. So we could get rid of that, and so we get the map prediction rule, which is argmax over y, p of x given y times p of y. Very often people confuse this with map learning. Map learning is where you are doing argmax over the entire hypothesis space and trying to find find a classifier that is most probable given a data set. In map prediction, you assume that you have the classifier and you try to find the label that has the highest probability. And this can only work if your classifier knows how to predict probabilities. Right? Basically, these two terms here together define your classifier. So let's examine this slightly more closely. We want to predict the label that has the highest product of the likelihood and the prior. What do the likelihood and the prior mean in this case? The likelihood says, what is the probability of observing this example if the true label was what? What is the probability? For example, for instance, you can ask, if the true label is spam, what is the probability that this would have been an email? This email is the one that I would get. That's the likelihood. The prior is asking, what is the probability that the label is what? What's the probability, for example, that an email, before you even see any input, is a spam email? What fraction of your inbox is spam, basically? That's what it's asking. And the prediction is the product of these two things, and you take the argmax. So effectively, in order to define a probabilistic classifier, all you need are these two sets of probabilities. You need the likelihood and you need the prior. Questions?
So we are going reverse from output, we are predicting the example.
Yes, we are not predicting the example, we are asking what is the probability that if this were the output, this example would have been constructed. And the only reason this works is, the only reason this is correct is because of Bayes' rule. It may seem a little counterintuitive, but once you look at how it comes up, it's mathematically correct because you just apply Bayes' rule. And this was also the same observation that someone had in the last lecture. It seems like we're going reverse. Instead of asking what's the best classifier, we're asking something about the probability of a data set given a classifier for map learning. Here we're asking for the probability of the likelihood of the example given the label. Yes?
So we're kind of learning the predictive power of the observation.
You could,
To what degree an observation predicts an outcome?
to what, yeah.
Per hypothesis?
No, this is the hypothesis.
Okay.
These constitute your hypothesis. If you have these numbers, you have your classifier, right?
Yeah, but you would have a likelihood of assigning label per hypothesis, right?
Yeah, but the hypothesis is implicitly present here. The hypothesis is the probability.
Okay.
The probability functions are your hypothesis. So your hypothesis space now consists of these pairs of functions. These probabilities are also functions, right? So your hypothesis space now consists of these pairs of functions. If you learned, our goal now is to learn these two probability sets, these two sets of probabilities. Our goal now is to learn a likelihood function and a prior function from a data set. Because your classifier is now probabilistic. Questions? Now, this can be a little confusing, so let's go through an example. Let's look at this data set that we looked at the beginning of the semester. Actually, we'll start off with a much weaker version of this. We want to decide whether we should play tennis or not. The prior probability, so we need two terms. We need P of y, that's the prior, and P of x given y. This is prior, and this is likelihood. The prior probabilities could just be a table that, this is an example of a classifier. The prior probabilities could be a table that says, should you play tennis? What's the probability that I should play tennis? Before you even get any observations from the world. What's the probability that, and this is, before I even get any information about the weather, there's a 70% chance that I won't be playing tennis today. And then the likelihood says, on days that you play tennis, so the top part of the table here, on days that I do play tennis, what's the weather like? So the first row here says, when I play tennis, if I do play tennis, the probability that the temperature is hot and the wind is strong is 0.15, and so on. The second part of the table here at the bottom asks, on days that I don't play tennis, the probability that the temperature is hot and the wind is strong is 0.4. The table these two tables at the bottom together constitute the likelihood. This is asking what's the probability of x given y? What's the probability of observations given that y is yes or y is no? Given that you play tennis or you don't play tennis. If you had both these sets of numbers, then I can now ask what is the probability that I should play tennis on a day that is, say, cold and strong. On a day, so I could ask, what is the probability that I might have that? Yeah. So let's say if you have these two sets of numbers, or these three sets of numbers actually, you could ask what's the probability that you should play tennis when the temperature is hot and the wind is weak. And the way you do that, the map prediction could be the product of the likelihood and you first compute the product of the likelihood and prior for every value of play tennis. So in other words, you ask what's the probability of the temperature being hot and the wind is, so you ask what's the probability of x given y times p of y. you compute this quantity for all possible values of y, because y is the quantity we care about. So you compute that for y equals yes or play equals yes, and here you just look up values in the table. When play equals yes, this part of the table comes from the top. This number comes from the top, so it's actually from this row here. Times probability of yes, that's this quantity here. And you multiply them, you get 0.12, and then you do the same thing. The probability of hot, weak when it's no is from this. When you don't rate tennis, is from this entry here, and this comes from the prior. You multiply those things. You ask what's the which value of play has a higher value, higher product, and it turns out, according to this method of classification, you say if the temperature is hot and the wind is weak, then you play tennis. Why? Because this 0.12 is higher. This is how maximum a posteriori prediction works. In order to do maximum a posteriori prediction, we need both these tables. In other words, all these numbers, these 10 numbers together here, constitute our hypothesis space. The job of learning is to fill in all these entries. Once you have all the entries, you can mechanically predict. Questions before we talk about the learning part? Yes?
This is probably just sort of restating things. I just want to make sure I understand. So, I mean, that top table tells us that, I mean, it's a lot more likely that you're not going to play tennis on
In the absence of any information.
Right, but then using this method, we can determine that under these certain conditions, it's actually more probable that we
Yes,
can play
yes, that's exactly right. That's exactly right. The prior says you should not be playing tennis in the absence of any information. And then we get some new information and suddenly we're playing tennis. Yes.
Then the entire prediction will depend on the prior, right? Because the likelihood for a given data set, the likelihood is going to remain the same for every hypothesis. So your hypothesis will basically be just.
It depends on how strong your prior is. If, for example, your prior was 0.5, suppose, then it doesn't change anything. Think of the prior as being very similar to the bias value in your linear classifiers. The bias does not look at any of the features, right? In the absence of any information, the bias makes the entire decision. The prior is very similar to that. You had a question.
So how do we get these values P, T, W, tennis equals?
How do you get those values?
Using the learning technique we studied earlier?
No, we're going to talk about that now. We're going to, we need to learn these values, and learning these values is the next thing. Yes.
So normalizing the 0.12 and the 0.07, we normalize that would give us our percent probability.
That's your probability. That's actually your posterior probability. The posterior probability of yes is 0.12 plus 0.07, and 0.12 divided by 0.19.
So that would give our forecast percentage if we normalize
Yes, exactly right. Exactly right. Okay, good questions, and let's move ahead. So the map prediction is yes, so no surprise there. So all we need to do now is to learn these numbers. Let's think about how hard it is to learn these numbers. So this is the entire table that we saw when we were talking about decision trees, and let's count how many entries would the table have. If we had to learn, would the two tables have, would the likelihood and the posterior probabilities have. So we have a label, play. So first question, how many entries do you need to define the prior probability? And I argue it's just one number, by one. Prior probability is just one number. Yes?
Other is 1 minus that.
The other one is 1 minus probability of not playing is 1 minus probability of playing, so you just need one number to define the prior probability in this case. So that's easy. For the likelihood, there are 4 features here, and I think each feature here takes multiple values. I can't, let's see, this one takes 3 values here, this one can take 1, 2, 3, there's H, M and C. This one takes 2 and this one takes 2. So the number of parameters that are needed would be, so we need probability of X given play equals plus, and probability of x given play equals minus. This is this the each of this is the we need two of these tables. The top table has how many entries? Actually, there's a mistake here because this cannot be 4. The top table has 2 times 2 minus 1 entries. For every possible combination of the features, we need 1 entry in the table. Minus 1. Why minus 1? Because they all add up to 1. So you need those many minus 1. So you have, what's the product there? 35 numbers for probability of x given play equals plus. Probability of x given play equals minus requires maybe an entirely different set of 35 numbers. Right? Because that's a different probability distribution. So, is this counting argument clear? In order to learn this classifier, you need 35 plus 1, 71 numbers. Once you have those 71 numbers, you can train the classifier. You basically finish training and you can make predictions. Does the counting argument make sense? Okay, that seems okay, just 71 numbers. Let's say you have k labels, not 2. Then you'll need k minus 1 for the prior. You need k minus 1 numbers for the prior. Because if you have k labels, let's call them without, in general, let's call them 1, 2, 3, all the way to k. Then you will need probability that y equals 1, probability that y equals 2, and so on. So you need k minus 1 numbers for the priors. And for the likelihood, let's say you have d Boolean features, not 4, but d Boolean features. You need 1 number for every combination of those features. So you will need k times 2 power d minus 1. Why 2 power d minus 1? Because the last number, it's a probability, so the numbers have to add up to 1. You have 2 power d numbers that add up to 1, so one of them you don't need to remember. And you need 2 power d minus 1 parameters for every possible value of the label. For the likelihood, right? Because we need p of x given y. So for every value that y can take, we need a different table. Earlier we had only 2 labels, so we had 2 tables. Now we have k labels, so you have k tables, each one that's exponentially large in the number of features. So basically the punchline here is that you need a lot of numbers. If you have d features, you need an exponentially large number of parameters to learn these kind of classifiers. Questions? Yes?
So this idea of multiple tables is, why did we require 2 tables?
Why do you require 2 tables? Because you need one table that says for when the label is yes. You need one set of likelihoods. So one set of likelihoods when the label is yes, because that's one function. The other one is when the label is no. And these two need not have anything to do with each other, right? Because they are different functions. If you have 2 labels, you have 2 sets of likelihoods. If you have k labels, you have k sets of likelihoods. Other questions? Yes?
Can you calculate likelihood from the training set?
That's the hope. That's the point. That's what we are going to do with learning. The problem is how many examples do you need to learn these many parameters? So the entire classifier, the hypothesis space, is defined by k minus 1 plus k times these many numbers.
Why do we have to calculate all of them?
Well, that's your classifier, right? If you make a prediction, in order to make a prediction, you need all those numbers to make a prediction.
So I mean, for a given example that we want to label, we just need
We will just need one of those you need one entry for each table in the likelihood, plus one prior. Actually all the priors. So for a given example, you will end up using only 2k of these numbers. But you don't know which example is going to show up in the future, so you need all of them. That's your hypothesis. You look perturbed.
But how, it seems unlikely that a data set's going to give you all of these.
It's practically impossible.
Right. So,
Yes. So,
give up.
that's a good question. That's a very good question, and that's, yes.
But couldn't you just say that all of these things are equally probable, and then for the things that you have, you calculate probably,
So,
and then you have a
right, so you've made an assumption. You made an assumption that says, if something is not attested in the training set, then I'm going to just give it some default probability. If it shows up in the training set, I'm going to use the probabilities that I calculate from the training data. And then I normalize and hope this reflects real life. Right? That's one thing. But in general, there is another issue here. If you really care about generalizing, this method, if in the absence of any other tweaks, you have an extremely large number of parameters. You have an exponentially large number of parameters. And what we know from our stories with VC dimension and stuff, VC dimension did not care about whether your classifier is probabilistic or not. VC dimension was a general concept. The theory of learning tells us that if you have a large number of parameters, you're going to have a hard time. It's going to have high VC dimension. You need a ridiculously huge number of training examples to generalize. So, in using words that we saw in the last week, if you have a large number of parameters and very small training data, I mean, if you have very few training examples, your classifiers are going to have high variance, because if you change the training set just a little bit, your learned classifier is going to change entirely. So your models are going to have high variance. So it seems like a hopeless situation. I need to learn a huge number of parameters, and no training set is going to be enough to give me the information that I need to fill up those tables. How do you deal with this? Any ideas? Yes?
Would it make any sense to, rather than like, if you have y equals 1, what's the probability of seeing all of the features exactly like that? Instead you do if y equals 1, what's the probability that it was thought? You only take like one feature?
You take some of the features, maybe?
Yeah.
So, in order to make that work, so that's a good idea. And in fact, that's the idea that I'm going to continue with. But let me repeat what you just said. What he said was, would it make sense if instead of remembering that row entirely, so for probability of y equals 1, I want the entire feature vector to be generated exactly. What if one of those features changes? Should the probability change a lot? Maybe not. So just to build this intuition, let's say you have 4 features, x1, x2, x3 and x4. And the likelihood is asking what's the probability of this given y equals, let's say, yes. Let's say I have x1, x2, x3 and x4 are all 1s. And this will correspond to a number. Let's say this is 0.7. Let's say, or 0.7 seems too high, let's call it 0.1. Now let's say one of these features changes. Would this be close to 0.1 or not? Maybe it should be close to 0.1, because only there's a slight change. Instead of 4, let's say you have 4 million features and only one of them changes. Maybe the probability should not change too much. In other words, what you're saying is that you're actually, in order to formalize that idea, you need to introduce some idea or some notion of independence. The way to, or in general, the only way that we know of dealing with this possible explosion of the hypothesis space is to make independence assumptions about this probability distribution. What does that mean? Let's kind of review what conditional independence is. Suppose you have 3 random variables, x, y and z. The variable, the random variable x is conditionally independent of y, having observed z, if the probability of x given z is the same as does not change whether or not you observe y. The probability of x given yz is the same as probability of x given z. In other words, x does not care about the value of y. The probability of x does not really care about whether or not you observe y if you knew the value of z. So the way you say this is x is independent of y given z. I hope you've seen this before at some point. And another way of saying that, equivalent way of saying that is probability of x comma y given z is the same as probability of xz and probability of yz. So this is a functional this is an assumption about the nature of the probability distribution. Or this is at this point it's just a definition. We are saying that x and y are conditionally independent of each other. If you knew the value of z, x and y don't depend on each other. And this is the formal way of defining that statement. Seems familiar? Have you seen this before? Has anyone never seen conditional independence? At this point, if I ask the question that way, nobody's going to raise their hands. Anyway, please go back, and if this doesn't seem awfully familiar, please go back to your, I don't know, first grade or something where you learn this stuff and refresh this material. Turns out, conditional independence is the tool that we'll use to make our lives easier, to make learning possible at all. So you have d features, and the likelihood function says what's the probability of observing these d features given the label. And it required exponentially large number of parameters. Instead, we could ask, you have d features, but what if all the features were conditionally independent of each other given the label? In other words, we are asking what if, this is an assumption, all our features are conditionally independent of each other given the label. In other words, this massive likelihood function is decomposed as the product of smaller likelihood functions. Probability of, if you knew the label, then the probability of x1, then x1 and x2 and x3, all of them are conditionally independent of each other. Turns out, let's count how many numbers we need. If we did not make that assumption, we needed k times 2d minus 1. But there are only d numbers here for each value of y, and we have k values of y. So you have only d times k numbers to remember. So by making this conditional independence assumption, we have reduced the size of the hypothesis space from exponentially large number of parameters to just kd parameters. So this assumption is called the naive Bayes assumption. It's naive because what is the assumption? It's naive because this assumption is almost never true in real life. It's saying that think of a spam detector. If your email is spam and you have the words, say, free and I don't know, antivirus in your email, then this assumption says the probability of observing free in your spam email is independent of whether the word antivirus shows up or not. And in practice, this is almost never true, but it's a convenient assumption that we make to make our math easier. So this is called the naive Bayes assumption, and this is what we'll use to, these are the parameters, the kd number of parameters that we'll train instead of the exponentially large number of them. Questions about this before we get into, yes?
It's from the previous slide. How are we getting that 2 power d?
Okay.
Because it, how did that 2 come? Where did that 2 come?
Oh, because we assume that each feature is Boolean.
Okay.
We assume if each feature is Boolean and you have d features, then you have 2 power d possible combinations. So this is the naive Bayes assumption, and this is something that you should be extremely comfortable with going ahead, because we will keep referring to this all the time, at least for the next 20 minutes and probably the next 20 minutes of the next lecture, first 20 minutes of the next lecture. So the naive Bayes classifier is a classifier that makes this assumption. It assumes that all features are conditionally independent of each other if you knew the label. So in order to predict, earlier, remember, all we needed was the prior, which was P of y, and we needed the x1, the likelihood function. We needed that, but by the naive Bayes assumption, we have reduced this into the product of each feature, the probability of each feature given y. So all we need are the priors, and for every feature we need a likelihood of that feature, the likelihood function for that feature given the label. At decision time, we're still going to do the same thing. We're going to predict. The classifier is going to try out every possible label like we did for that tennis thing, and compute the value of the product of the prior and the likelihood. But now our likelihood has decomposed into this product itself. So we are now calculating the product of the prior and product of the class conditional probability of every feature, the label conditional probability of every feature. So this is your naive Bayes classifier. You try out all these possible values, and then you pick the label that has the highest quantity, the value here. Before going ahead, questions? And I'll let you stare at this for a minute or 30 seconds so that you can manufacture questions.
So if the assumption is almost always wrong, I mean, how good is this?
Oh, that's a brilliant question. I have no idea. So the assumption is almost always wrong, but this classifier is often shockingly good. So that suggests that there's something fundamentally interesting happening about the domains where we apply this classifier. So spam detectors, for example, the first spam detectors were often naive Bayes classifiers. It turns out that today spam detectors are way more complicated, but this is such an easy the classifier to train that people ended up using this, and it worked shockingly well. It was obvious that the naive Bayes assumption was not true, and yet this classifier worked pretty well. And there have been a few attempts at explaining why, by reasoning about the space of all probability distributions and how the set of probability distributions that satisfy the naive Bayes assumption is densely located in this entire space, but it's not entirely satisfying explanation. It works shockingly well.
And then one more question, is this at all applicable to regressions?
Yeah, sure. You could make, I have not said anything about what this P or what the Y is, right?
Right.
If Y were real numbers, you could make the same sort of an assumption. You would have Gaussians, for example. You could have Gaussian distributions over the Y. Yes?
So we also get a confidence of our label out of this as well.
Out of any probabilistic classifier. Does not matter, it's naive Bayes. Right? I could have done that for any probabilistic classifier. It turns out, even with your SVM perceptron type classifier, you can get a confidence estimate. The way you do that is how far is it from the separating hyperplane. If it's very far from the separating hyperplane, you're more confident. And that intuition actually becomes more concrete when we talk about logistic regression. Okay. Yes?
Does that, does this thing also remove the necessity for a very large data set which was required?
Yeah, because you only need KD numbers as opposed to K 2 power D numbers. You have only a smaller, you have a smaller hypothesis space, which means you need smaller data set to train. And that is the reason why you make this assumption in the first place. So that's nice. So you have the naive Bayes classifier. Let's ask ourselves, you have a classifier. If you were doing binary classification, what is the decision boundary of the naive Bayes classifier? Decision boundaries are, everything that we learned before still applies, right? I mean, you have you have D features, which means your features are D-dimensional points. I could ask myself, how does this naive Bayes classifier slice up this D-dimensional space, and how does it cut the space of D-dimensional points into positive and negative, for example? The decision boundaries for linear classifiers were trivial. We made the assumption that the decision boundary is linear. Let's see what happens here. So it's kind of easy to analyze this if you have only two labels. So let's do that. You predict the label is positive if how do you predict the label is positive? You predict the label is positive if this quantity times this quantity for the positive class is more than the same thing for the negative class. The prior times likelihood for positive is more than the prior times likelihood for negative. Then you say the label is positive. But we can bring this down, the left hand side, we can bring one side down, and you predict the label is positive if the prior times likelihood for positive divided by the prior times likelihood for the negative is more than 1, assuming there are no zeros here. Let's assume there are no zeros. I could rearrange this term. I could rearrange this thing and say I can keep this together, so it is P of y equals plus divided by P of y equals minus times the product over all features. This should just be xi, j, let's say. Let's make this greater than equal to. I've done nothing here. I've just used from going. If the naive Bayes assumption is true, this is true. Now, at this point, in order to reason more about this, you need to start asking what is the functional form of this P? What do these P's look like? Turns out that in many cases, if you simplify this for certain interesting functional forms, this ends up becoming some weights transpose the feature vector plus some bias. If you take log, actually, the way to see this, if I take log of this quantity is independent of any feature. That becomes the bias term, and the rest of it ends up becoming a weight. I have written this up more in detail in a note on the class website, so I encourage you to go through this. What is interesting here is that the naive Bayes classifier, the decision boundary, is still linear. If you are learning a naive Bayes classifier, you are effectively learning a certain linear function. We did not start off with any linear classifier. We just ended up with a linear classifier, and not only do I encourage you to go through this proof because it's actually fairly simple, your homework might actually require you to go through that proof, so there's more reason to do that. So your naive Bayes classifier is just linear, so I could have trained this as a linear classifier as well, right? I could have just forgotten all about this, just run, say, SVM or perceptron. But actually it turns out that's not quite right. Even though the naive Bayes decision boundary is linear, if you train a naive Bayes classifier, your hypothesis space is not the set of all possible linear classifiers. It's actually a subset, and that's another reason why typically if you train a naive Bayes classifier, say for spam detection, and you compare it against, say, an SVM sort of a classifier, the naive Bayes tends to do slightly better. Sorry, the SVM tends to do slightly better because you are allowing the SVM to explore a larger hypothesis space. Alright, so let's just summarize where we were. I talked about the naive Bayes classifier. The naive Bayes, and it's entirely driven by two important concepts. The first one is the idea of a probabilistic classifier, the classifier that can predict probabilities and then you take probabilities over what? Probabilities over labels. Given an example, and you take the label that has the highest probability. One such classifier is an naive-Bayes classifier, which makes this rather strong independence assumption about the features. The features are conditionally independent of each other given the labels, and using that we can define the naive-Bayes classifier. At this point, I have said nothing about learning. I have only defined the hypothesis space. I spent 45 minutes today defining a particular hypothesis space, which is longer than I spent on any other hypothesis spaces. So let's talk about how we learn classifiers in this case. The hypothesis space is entirely defined by the collection of probabilities. We have, if you have a binary classifier, you have one number for the prior, P of y, and you have k d minus 1 likelihoods, or 2 d minus 1. Twice d minus 1. Is that right? Yeah. You have those many likelihoods, one for each feature. The learning setting is the same. You have a bunch of, you have a data set, a bunch of examples with labels, and you want to learn all these numbers. And now comes the interesting part. We want to learn the classifier from this data set, and let's say we want to learn this classifier using a probabilistic criteria. What's a good probabilistic criterion to learn classifiers? How do you learn classifiers in a Bayesian way? How do you decide that a particular hypothesis is better than another? How do you define best if you are Bayesian? Give me a name. Map learning. You could do map learning, maximum posteriori learning, or maximum likelihood learning. Let's do maximum likelihood, because I don't want to comment on any posterior probability on the priors over the hypothesis space here. So the maximum likelihood estimation for the naive-Bayes classifier would say, okay, I have a data set and I want to find the classifier that has the highest likelihood. So I want to find that has the highest likelihood of producing this data set. And I use the notation H here to define the collection of all the probabilities that we want to compute. H is this bucket of all these numbers. In the list, if you read papers about this, typically for probabilistic classifiers, people use theta to define all possible parameters. I'm using H just to keep continuity from the rest of the semester. So our goal now is to define this, find the numbers that define the classifier. So remember that. So in other words, you have a data set and I want to find the classifier that has the highest likelihood. But the data set itself consists of m examples. x1, y1, x2, y2, and so on, xi, yi. And we assume that, as we have always done through the semester, we assume that each example is independent of all the others and identically distributed. So all examples are generated IID, which means I can ask the probability of generating that entire data set given the hypothesis is simply the probability of the product of the probability of generating each example. So the data, this is the same as probability of x1, y1 and probability x2, y2 all the way to xm, ym given hypothesis. And we assume that each example is independent of all the other examples given the hypothesis, so we can write this term as this product. And this is what we've done all the time. We've assumed that all examples are IIDs, so we just say the probability of seeing a data set is simply the product of all these probabilities. Okay. Each term here inside this product is asking, what is the probability that a particular classifier, a particular set of naive-Bayes parameters would assign the label yi to an example xi. Okay? Questions? Before going ahead, are there questions? Because very soon this slide is going to fill up with notation. I'll be optimistic and assume that there are, yes.
So that X is the entire feature vector, not a single feature?
Yes, bold X means the feature vector, that's right. So exactly right. So we have two kinds of independence assumptions in play here. One of them is the naive Bayes assumption. Each feature value, each feature is independent of all the other features for the example. This independence, that's the naive Bayes assumption. This independence assumption says every example is independent of all the other examples given the hypothesis. This is assuming that the data set is generated IID. Okay, but at this point we can start, being mechanical about what we know. And in fact, from here we know everything that up to a certain point. This quantity here, I know that P of A and B given C is exactly the same of P of A given B C times P of B C. That's exactly what's going on from here to here. P of x y given h is P of x given y comma h times P of y given h. Right? Okay. But probability of x given y and h is simply the collection of tables, a collection of numbers. Imagine that that's those sets of tables that we saw, all those probabilities. If you had all the probabilities, I ask, this is exactly the first term here in the blue box is exactly the likelihood of seeing that label. Sorry, likelihood of seeing that example given the label. And now the naive Bayes assumption kicks in. The probability of seeing that entire feature vector given the label is simply the product over all the features of the probability of seeing each feature given the label. And that's the naive Bayes assumption. And now what? So we've remember we wanted to find the maximum likelihood estimate, and this is the definition of, the definition of maximum likelihood was we want to find from the hypothesis that maximizes the likelihood, and from here to here we said that all examples are IID. And from here to here, it is just, there's nothing, no magic going on, this is just a definition. And here to here, it's the naive Bayes assumption. Now what? I want to maximize this massive product. What do you do when you want to maximize products? Take log. Why? Because it turns out we just have we know how to handle summations better. So you take log. Do you want to take a picture of that? There's a video, don't worry. So there's a log. You take the log. You take log and you just convert all the products into summations. And so, in order to get the maximum likelihood estimate, all you have to do is maximize this entire sum. It's exactly the same. Now what? At this point, we want to find the maximum value of the sum, but we've gone as far as we possibly could without actually commenting on what these P functions look like, what these probability functions look like. At this point, we need to make an assumption about the functional form of these distributions. Because you can have different kinds of probability distributions and the behavior will change. I need to know what exactly these P's look like. The simplest form, which I have 3 minutes, maybe I can try to at least define this thing and we'll pick up from this in the next class. The simplest thing, let's assume we have two labels, 0 and 1, and let's assume that all features are binary. And I can also assume that this prior probability for the feature is simply, it's like a coin toss. It's defined by a single number, P. So the probability that the label is 1 is P, the probability of label being 0 is 1 minus P. So as part of our learning, we need to figure out what's the value of p. If you knew the value of p, you've defined the function. Similarly, I assume that each feature is Boolean as well. So I can define the likelihood in the following way. Let's just look at the first line here. I can say I assume that the probability that the label is 1 when the feature is probability that the jth feature is 1 when the label is 1, let's call it aj. Which means the probability that the jth feature is 0 when the label is 1 is 1 minus aj. I'm making an assumption here. I'm saying that this is how I believe the world works. Similarly, I can say that the feature being 1 when the label is 0 is bj, and the corresponding other side would be 1 minus b. This is an assumption. So on this slide, what I have is an assumption about the functional forms of this term here, the prior, and this term here, which is the likelihood of a feature given the label. And once we plug this in, we can now, so the job of learning is to figure out what is the value of all the A's, all the B's, and the P. So the hypothesis, H, is completely defined by these three sets of numbers, P, A, and B. Does it make sense? If you knew the P, the A, and the B, learning is done. So in some sense, finally we've brought learning to a more concrete situation where we can ask what are the values of these numbers, and the learning we can write down or try to invent learning algorithms that find these numbers. In order to get there, we have made so many assumptions along the way. We assumed that we had the naive Bayes assumption, and then the second assumption that we had was that the probabilities take this functional form. In the next class, we'll start off with actually solving this maximization problem for this functional form, and that will give you your learning algorithm for the naive Bayes classifier. I'll stop for questions if you have any, otherwise I'll see you on Tuesday. This is a lot of material, so please go back and convince yourself that you understand what's going on. It's very easy to get lost in this notation, so it might require a couple of passes over the slides if you've never seen this before.
So, you wanted to do the H, where is H coming in here?
Sorry?
Are they going to maximize that all of the AID and H?
Yeah.